One of them is to use triangles. You may have seen a little bit of trigonometry before. It can be introduced using triangles. The other one is to introduce it with the unit circle, and that's what this book refers. So if you saw it before introduced with triangles, this is going to do the triangles as a special case of the unit circle. The other approach is start with the triangles and do the unit circle as a generalization of the triangle. So we'll do that one. This book's. And we'll say, suppose we take a unit circle, which means a circle of radius 1, and for simplicity, we put its center at the origin. So the unit circle generally assumed to be at the origin. Put it up at the origin with angle theta in standard position. The initial ray is along the positive x-axis, counterclockwise against the direction the clock moves is positive. Counterclockwise is also the direction you run around the track if you ran track before. Has this way of defining 6 trigonometric functions. Put them up here so I can get them all on. We'll define the sine of the angle theta to be the y coordinate on the unit circle. So it defines by xy the intersection of the terminal ray with the unit circle. It's a mouthful, and you can tell I'm not an English major to write these run-on sentences. but it's not a bad sentence, actually. By the intersection of terminal ray and unit circle. Sine of theta is the y coordinate, and it's written out this way: sine of theta. But who wants to write SINE? We'll just write SIN, it's a little shorter. Or cosine of theta is the x coordinate. That's short for cosine. Those are the 2 most important trig functions of all, but there's 4 other very important ones also. All right, tan theta, you can see these on your calculator. That'll be y divided by x. Call that the tangent of theta. COT theta is x over y, is the cotangent of theta. SEC theta stands for secant of theta, that's 1 over x. And then finally, CSC theta, 1 over y, called the cosecant of theta. So there's 6 basic trig functions, and those are their definitions. Here's how you figure it out. You just take any angle in standard position. There's the initial ray. Here's the terminal ray. And here's theta to get there. It doesn't matter if you go around umpteen revolutions and wind up here. It just depends on the terminal ray. So I'll draw this one just going from here to here, but it could go this way, or it could go around 17 times and then land up here, right? You take this point right here, you give us x, y coordinates. You call the y coordinate the sine, the x coordinate the cosine, this one divided by this one the tangent, and so forth. In a picture worth 1,000 words, this probably meant nothing to you. Well, once you put the picture, it's easy, right? And that defines the 6 important trig functions that we know and love in trigonometry. There's others hardly anybody uses. I'll reference this page on Wikipedia to show you just for fun. But we aren't going to do anything but those 6, all right? When you see all this other stuff, you can just ignore it. I told you before, if you don't like your textbook or you just want a second reference or whatever, it's one good place to go is to just go Google Wikipedia on whatever topic it is, and usually there's some high-powered academic who wrote a really nice, careful article on this stuff, and you can learn from it here. So how I got to this one is I just Googled Wikipedia unit circle, and this is the first listing that came up. So I clicked on it, and here it is. If you take an angle and standard position, this has nice computer graphics, better than mine, and run the terminal ray out like this, the point of intersection, XY, tells you the Y coordinate is the sine of theta, and the X coordinate is the cosine of theta. So that defines the first two concepts, all right? Just the coordinates here. And I call these functions. Why do you think I call them functions? They actually are in the classic algebra sense. Remember what a function is in algebra? Just a rule, like f of x, right? F of x is a rule that when you give it x, it gives you out exactly one y, not two values of y, right? And it's not necessarily defined for all x. It might be the square root of x function. It's only defined for non-negative x, right? But for those values of x for which it's defined, it gives you out exactly one y. And so for that reason, it passes the vertical line test. But the idea is, I won't write it since we're trying to do. But for each value of the input, it gives you exactly one output. And that's what this does. If you give me any angle theta, it gives me the y coordinate. That's one output for each input angle. Right? You give me an angle, I give you the y coordinate. You give me another angle, I give you the other y coordinate. It's a rule that gives exactly one output to each input, so we can call it a function according to the definition in algebra. Similarly, for each angle theta, I tell you what the x coordinate is at the intersection point. That's a rule that gives exactly one output. All right. And now if you go down on here, you'll see the other trig functions defined. And it's kind of neat. The geometrical interpretation here, this is really the nicest picture I know of this. The geometrical interpretation you don't need to know, but I just wanted you to see it for your education. You do get extra stuff by coming to class rather than just reading the book. Here's what the tangent is. If you take, here's the unit circle, right? So unit radius, that's what circle means. I should have marked it on my picture. And you drop a perpendicular to the x-axis to get the y coordinate. You then go over to get the x coordinate at that point. The x coordinate is cosine. They left off the theta just for brevity. And the y coordinate is sine. Right? Now, what should the other things be? And you might be interested in taking a tangent line to the circle at this point of intersection, right? If you take the tangent line and go over to the x-axis, we call this length the tangent of theta. So this is y the sine, this is x the cosine. These do have geometrical interpretations. This is the tangent. But that's not the way I wrote the definition. I wrote the tangent as y over x. How is that? So you see the tangent actually does have a nice geometrical definition, just like sine is the y coordinate, cosine is the x coordinate, tangent is the length of this line segment, plus or minus. It actually can be negative. It's the position on the x-axis. It depends on the position on the x-axis, but and y-axis. But it's plus or minus this length. What you do is you look at this triangle right here, right? And if I'm going to define this length to be the tangent, then I'll say, well, this side of the triangle over this side of the triangle, since this is 1, is also the tangent, right? Take tangent divided by 1. That's the ratio of the long leg to the short leg of this right triangle. But if you turn it around, it is similar to this right triangle, right? You have the same angle here in this triangle as you do in this triangle, right? That this angle occurs in both triangles, and they both have a right angle. It follows that the third angles have to be equal. This triangle and this one is similar, right? So now you say the tangent, this side to this side of the big triangle, has to be the same as this side to this side, the long leg to the short leg in the small triangle. Oh, that's y divided by x. So equivalently, the saying that this distance is the tangent is to say y divided by x is the tangent. So you say, why do you define tangent by a ratio of y to x? Well, it actually has geometrical significance because it's equal to this length here, plus or minus. And then cotangent is actually this length here. And if you look at this triangle, this one's also similar to this one. And the ratio of this side to 1 is the same as ratio of this side to this side. Short side of the triangle to short leg to the long leg, short leg to long leg. And it's cosine over, it's x over y or cosine over sine. But x over y is how we can define the cotangent. And then this length here along the x-axis, if you call where the tangent line intersects the x-axis, we can call that cosecant. And using this other big triangle here, let's see, this one. No, I want this one. And take this over 1, this cosecant is the same as 1 over x. I won't go through the details. You don't need to know this picture. I'm just saying that what motivates taking y over x or 1 over x is it actually has geometrical significance with regards to the unit circle. Once you take this tangent line and find its intersection point, this is secant, the x-coordinate where the tangent line intersects, and the y-coordinate where it intersects is the cosecant. And so all 6 of those have geometrical meaning. All right, and then there's some other ones, verse sine and all these. Those ones nobody uses. So look at this thing, just ignore them. With this definition, let's try and make some actual computations of trig functions. I can turn this off now. Believe it or not, we can actually compute exactly all 6 of these trig functions of any special angle. Remember what a special angle is? Trigonometric function. Those are the 6 trig functions right there. Any special angle. And we said the special angles were those that are multiples of 30 or 45 degrees. And you'll see why we want to call them special. Well, multiple of 30 degrees, 5 degrees. Or both, right? 90 degrees of multiple of both, for instance. Here's a simple example. What if I wanted to calculate sine 90 degrees? What would I get? I can figure it out on the unit circle exactly, right? Draw the unit circle. I draw angle and standard position up to 90 degrees. I can put that right angle bracket if I like. But there's 90 degrees. And I take the terminal ray and it intersects right here. What's the coordinates of the point? Yeah, 0, 1, 1 on the y-axis, right? And it's a circle of radius 1. It goes up 1 unit, it goes through the point 0, 1. And now I know from the definition of sine and cosine that whatever the x-coordinate is cosine of the angle that got you there, in this case 90 degrees. And whatever the y-coordinate is, that's the sine. Right? So every point, any point in any angle theta is cosine theta, sine theta. I should have marked this here. Xy equals cosine theta, sine theta. It's on Wikipedia. That's how they're defined. The y-coordinate, the x-coordinate is cosine, the y-coordinate is sine. The reverse order, right? Cosine first and then sine. And so I know immediately the sine of theta from this picture is by looking at the y-coordinate is exactly 1. Easy. Right? And I get cosine at the same time. But I can get all 6 trig functions, and I take, for instance, from that picture also the cosine of 90 degrees. The x-coordinate is 0. What's the tangent of 90 degrees? Tangent is supposed to be y over x. That's its definition. So that's 1 over 0. Uh-oh. What do I do with 1 over 0? It's undefined, right? Division by 0 is undefined. Remember, functions are not necessarily defined for all possible inputs. Tangent is not defined at 90 degrees. But when you get a division by 0, you simply say this function isn't defined for that angle. Sine and cosine are defined for all angles because they're just the x and y coordinates, right? But these ones that are quotients are not defined at certain angles when you get a division. Okay. How about the cotangent? Despite that the tangent is not defined, the cotangent is the reciprocal. It's x over y, and x is 0 and y is 1. This quotient is 0. So the cotangent is defined at 0. What you'll find is an angle that lands on an axis. We call those quadrantal angles. Two of the trig functions will always be undefined because they'll get it at 0, but the other four will be. Happens in practice. And then the secant of theta, the secant of 90 degrees, 1 over the x coordinate. Well, the x coordinate is 0. Undefined, right? So the secant and the tangent are both undefined. But now the cosecant of 90 degrees is 1 over the y coordinate, is 1 over 1 is 1. So in any quadrantal angle, two trig functions will be undefined. Okay. However, actually any special angle, right? This is a special angle. It's a multiple of 30 and 45 degrees. Any special angle, we can compute the trig functions exactly by instead drawing what we call a reference triangle. Evaluate exactly all these trig functions, for instance. What is the sine of 45 degrees, do you think? Well, you just have to draw the unit circle and you figure it out, right? The sine is the y coordinate, we said. So I draw the unit circle. I take an angle in standard position. This has to be 45 degrees. I drop the perpendicular to the x-axis. It turns out you can compute this just as well dropping to the y-axis, but nobody does it. Everybody drops to the x-axis. Always drop their perpendiculars that way. Every textbook does it. And the reason is just for convention, right? Some people decided, I'll just write my words backwards, right? How could you ever read it? It'd be really hard to read. Everybody writes left to right. So it's just so everybody drops the perpendicular to the x-axis so everybody else can read it easily, right? If I drop that here and I take that perpendicular I drop plus the terminal ray out to the unit circle. So this is length 1 because it's a unit circle. And then I close the triangle by moving along the x-axis. We get what's called the reference triangle. And this angle at the origin within the triangle, we call the reference angle. Now, if we chose a special angle here, a multiple of 30 or 45 degrees, this reference triangle will always be one of our two special triangles, either the 30, 60, 90, or the 45, 45, 90, or you'll get a quadrantal angle to be obvious. So you get a special triangle or a quadrantal angle where you get it immediately like the last example. In this case, what's this angle here? 45 degrees, right? This angle was 45. And this one's 90 because we dropped the perpendicular. In order to add up to 180, this one also has to be 45, right? 45 plus 45 plus 90 makes 180. So this is a 45, 45, 90 right triangle. I know that when I memorized it. So that's why I told you. What I do is I take the one that I said was more important to memorize for trigonometry, the one with 1 for the hypotenuse length, and I draw it wherever I want. Here's my 45, 45, 90 triangle. I memorize the other two sides are square root 2 over 2 when the side is 1. Now I want to say if this triangle here is actually this one, then what is the sine of theta? It's the y coordinate. I can figure it, right? Here's the axes. The x and y coordinates are just square root of 2 over 2, square root of 2 over 2. The sine is the y coordinate, the sine of whatever angle's at the origin here. So I get that sine of 45 is the y coordinate square root of 2 over 2. Now maybe it seems a little complicated, but actually once you've done it a number of times, you'll find that you can picture this in your head and figure it in your head. There's also a beautiful picture. You can see it on, I should have kept it up here, on Wikipedia, that does all the special angles and shows all the different sines and cosines at each point. If you want, you can memorize that. I'll bring it up again. I think better than memorizing it, it's better to picture this in your head. That memorization tends to go away where this picture stays there, I think, longer. So here's how you can compute the sine of 45 degrees. Picture in your head the unit circle, drop a perpendicular with a 45-degree angle. Oh, this is square root of 2 over 2, the y coordinate. That's the sine. And you can do it without drawing the picture even. But for the beginning, draw these. And that's how you can compute it. Suppose I wanted to calculate now the cosine of 150 degrees. Once again, I'm in good shape. 150 is a multiple of 30, right? So it's a special angle. I can compute this exactly. I know it before I begin. How do I do this? I can draw it or just picture in my head. How do I sketch 150 degrees? This is a little trick here that you have to pick up today. To sketch any angle, particularly special angles, do this, pull out first whole rotations, pull out any whole rotations that there are in the angle. And you break it up into the sum of the whole rotations plus what's left. Then pull out any straight angle if there's one in there. And write what's left. Then pull out any right angle that might be what's there. Straight angle, there can only be one. Pull out all the rotations. Pull out any right angle if there's one left, and then sketch the fraction of the remaining right angle. So that's how I'm going to sketch this 150-degree angle. I'm going to say 150 degrees. There's no whole rotations to pull out because it's not at least 360 degrees, right? There's no straight angles because it's not at least 180, but I can pull out a right angle. So I'll write it at 90 degrees plus what's left, 60 degrees. Easy to sketch. I draw a 90-degree angle going to the next axis. Then 60 degrees is 2/3 of a right angle, right? 2/3 of 90 degrees. Break this up into thirds. Draw this one right here. There's 60 degrees. Now, the way people do this, it'd be kind of nice in this way to drop it to the y-axis. You know the angle immediately, but once again, books don't do that. They all drop a perpendicular to the x-axis. You take the perpendicular, you drop to the x-axis, the terminal ray out to the unit circle, which has length 1 always because it's a unit circle. And then you close the triangle by moving along the x-axis. Here's the reference triangle. Now, what is this angle in here, the reference angle? 30. Yeah, 30. 60 plus what equals 90? It must be 30 degrees. There it is. So that's the reference angle. And by the way, reference angles are always positive, even if they're down here. The reason being that we always call angles in triangles positive. You don't need negative angles in triangles, right? They're all between 0 and 90. So the reference angle is always positive no matter where the triangle is, because we're just talking about a triangle. And here's the reference triangle. Reference triangle. And I can figure out this one because I memorized it, right? When I have hypotenuse 1 and 30, this is the 30, 60, 90 triangle, right? 30 plus 90 plus what equals 180? This must be 60. The hypotenuse 1 makes the short side, the one opposite the small angle, 1/2, and the longer leg, square root 3 over 2. We just memorized that. So now I know the side lengths, and I'll mark them with positive numbers because they're side lengths of a triangle. Then the coordinates of this point are, well, let's say I went left here. The x coordinate is actually negative square root of 3 over 2, right? And the y coordinate is a half, because I went up, it's positive direction. So on the point coordinates, you put in the plus or minus, depending on whether you left or right, and up or down. But on the sides, I usually draw the side lengths. If you want to draw negatives here, calling them the coordinates, that's fine. When I draw it on the board, I'll draw the side lengths here. They'll always be positive. At the coordinates, I'll write the correct plus or minus. Right? But now I know immediately, this is the cosine, this is the sine of 150 degrees, just by the definition. Cosine 150, sine 150. But now you can see, it doesn't matter what angle you pick. If it's a special angle, it will always give you a special triangle here, or it'll be on an axis, and you can figure out exactly the coordinates. Cosine of 150 degrees comes out to be this x coordinate minus square root of 3 over 2. If you run this on your TI-84 calculator that doesn't do exact calculations, I'll tell you 0.8 something, 0.86 maybe. It will give you a decimal approximation. If you put that on your test, it's wrong. If I ask for exact answer, should have said evaluate exactly. If I say evaluate exactly, I'm saying minus square root of 3 over 2, not minus 8.6, whatever it is, 0.7. That's a rounded number. It turns out, maybe you remember from algebra, every square root of a whole number is either again a whole number, like square root of 9 is 3, square root of 16 is 4, or it's what we call an irrational number, a number without a repeating pattern that goes on forever. So no matter what place you cut off the decimal at, it's an approximation, right? You can't say, oh, there's a repeat, it just repeats this pattern. There is no repeating pattern. You can't say it ends here, it doesn't, it goes on forever. So all these square roots of whole numbers is either a whole number again or a non-repeating pattern that goes on forever. And it's not an exact answer if you stop writing your decimals anymore. Nobody can write forever, so you can write it this way, and that's the exact answer, minus square root of 3 over 2. So minus square root of 3 goes on forever, and minus square root of 3 over 2 also. Divide a non-repeating number by a whole number, and it's still doesn't. All right. So there's the exact answer for cosine of 150 degrees. And because it was a special angle, we got a special triangle, can figure it exactly. And sometimes it comes out to be an easy number, like in part A. And sometimes you get a negative on there. Now, we also need to be able to do these in radians. Suppose I wanted to do the tangent of 7 pi over 6. How about that? The tangent over here is defined to be y divided by x. Once again, once I'm good at this, I can just figure it out by thinking in my mind. I do this sometimes. But for now, what we'll do is we'll say 7 pi over 6, I need to break up into whole rotations. Is there a whole rotation in there? Not actually, right? A whole rotation is 2 pi. This is only 7/6 pi. 2 pi would be 12 pi over 6. This is not that big. Is there a straight angle in there? Yeah, there is, right? I can think of this as pi as a straight angle. This is 7/6 pi is bigger than pi, right? So it's pi plus something. What is it? Pi is 6 pi over 6. What do I need to get 7 pi over 6? Pi over 6 more, right? 6 pi over 6 and 7 pi over 6. Add the numerators over the denominator, you get 7 pi over 6. So this is another way of writing 7 pi over 6. It's a straight angle plus this angle. This is a special angle, right? We said any multiple of 30 or 45 degrees is a special angle. In radians, that's any multiple of pi over 6 or pi over 4. Since pi over 6 is a multiple, 7 pi over 6 is a multiple of pi over 6. This is a special angle. You know, we can do it exactly. And we can write it like this. So now what we'll do is the same thing we did before, but radians. We'll say pi is a straight angle. This is why you want to memorize, right? Straight angle is pi. And pi over 6 is 30 degrees, a third of a straight angle, a third of a right angle. So we break this up into 3 parts, and we go 1/3 of the way across the next part. Here's pi over 6, 30 degrees. It's nice to be able to convert them back and forth. Pi over 6 is a third of a ray. Now the reference triangle, I drop the perpendicular up to the x-axis. There it is. And so what are the lengths of the sides? Memorization, right? 1 square root 3 over 2. Oops. This is the short leg, 1/2 square root 3 over 2. So 1/2 always goes opposite the 30 degree. Now the coordinates must be negative and negative. So the coordinates of the point are minus square root 3 over 2 plus 1/2 and minus 1/2. And the tangent is defined to be the y coordinate divided by the x coordinate is minus 1/2 over minus square root 3 over 2. And I'll take a point off if you leave it like that. Why? Yeah, don't leave quotients with quotients. That's never simplified. And don't leave minus and minuses. It's like saying to your mom, it's not the case I'm not going to the movie, Mom. You cancel the minuses, I'm going to the movie. There you go. And now these twos cancel, since they're both denominators, but here's the careful way to do it. We say quotients of quotients are top times bottom over middle times middle. Same as top times reciprocal at the bottom, if you prefer that way. So it's top times bottom over middle times middle. Now the twos cancel. This is just 1 over square root 3. Will I accept that answer on the exam? No. I will, actually. I said this is the simplest way to write it. I will. But if you look at the answer sheet, you'll find out they always rationalize it. And multiply this top and bottom by square root 3. To rationalize the denominator, the bottom is now 3. And the correct answer, according to the key for your homework, the answers to your homework are mostly in the back, is square root 3 over 3. That's what you'll see. My answer wrong, it is right. You just didn't rationalize it. I'll take either of these on the exam. They're both correct in higher mathematics. But this is the one you'll find here. I'm going to get out of the exam a minute later. Okay? Let's just do numbers 1 and 2 out of 5.2. UCL stuff. One of those, that's this kind of thing, finding exact values of the graph function. And next time we'll get back to doing it on the calculator box.